Did you know that we can use Python to apply Beer-Lambert's law to our UV-Viz dataset? Let me show you. So here I've got a Jupyter notebook, a VS Code notebook that we're going to use for this tutorial. And the goal is to use Python to apply Beer-Lambert's law. And then I'm going to help you build the intuition of what's going on through a series of visualizations throughout this process. So we're going to begin by loading up our UV-Viz spectra. This is data that I have generated from ChatGPT, but it's a great way for me to model this work process. So I have my standards where I have wavelength, a standard 1 calibration, standard 2, standard 3, standard 4, standard 5. I have the concentrations that belong to those standards. So 2, 4, 6, 8, and 10. This could be any concentration unit. It does not matter for this set. And then we have an unknown sample where we have our UV-Viz data, but we don't know the concentration of this sample. And this is a very typical process in the chemistry lab or physics lab. And you can use Python instead of Excel to perform this analysis. So let's begin by importing our modules. So we're going to use NumPy, Pandas, and Matplotlib to do our data processing and data visualization. And then we have a new one, Statsmodels.api, that we're going to use in order to actually perform the calculations. So I'm going to begin by loading in my data and storing that data as standards df and concentrations df. So I'm going to take those two spreadsheets and import them. We can preview them really quickly so you can see how they come in. Here is our standards df. And if I replace this with conc.df, you can see what that looks like now. So we have our samples, whether concentrations or our standards. So the first step in trying to build a calibration curve for your data is to identify the lambda-max, which wavelength has the highest response in our data set. So I'm going to first show you what the data looks like. So let's just look at standard df.plot. You can see if you look across our data, we have values from 200 nanometers all the way to 400 nanometers. And of course, we would then expect our lambda max to be somewhere around 275 to 280. This is where we have the most amount of signal for our respective samples. I'm going to average out all of the data together. That is what this scd_df.mean will do. And then I'm going to chain IDX max to figure out which wavelength corresponds to the highest mean value. And then I'm going to print that statement as lambda max. And I'm going to update my plot to show you using a vertical line where the lambda max was based on these sets of functions. When we do this, we can see that the average data shows that we have a lambda max value at 279 nanometers. And we can see that corresponding vertical line here as a visual representation of what's going on in this process. So this is where we're going to get the most amount of sensitivity for our calibration curve. And so this is ideally where we want to build the model. Next, we're going to extract the absorbances from all of our standards at this particular lambda max. So we're going to take the absorbance value for each of our samples at 279 nanometers, and I'm going to call that standards. And I'm just going to return this as a NumPy array using the .values method. Then I'm also going to generate another array called concentration, where I'm going to just take my concentration column from my conc.df data frame and return that as an array as well. And I'm doing this to help me set up for our Statsmodels step in the next cell and allow for those variables to be very understandable. So now we're going to fit the calibration line. I'm going to use the Statsmodel add constant, and we're going to pass in these concentrations. And then we're going to fit an OLS model where we have our standards. We're going to generate this X array from our add constants, and then we're going to fit the data. Once we fit the data, we're going to output a couple of different parameters. One is the intercept at B0, and then the slope at B1. Then I will show you the summary of this model. From this OLS regression results, you see we have a lot of different data. We have our R squared. We have our constant at 0.0031. We have our X1 at 0.0995. We also have the standard error. We have some other outputs related to the confidence interval of our data and other ways to diagnose this model. So then I also want to plot this data so that you can gain the intuition of what's going on. To plot the data, we're going to use the OLS.predictX so we can see the output of this calibration curve. And I'm going to plot the scatter plot from the concentration and standards. And then we're also going to show how well the data fit using this OLS.predict. If we look here, you see that the model fits pretty well, and we expect this to be the case because this is a relatively small data set, and the way we've designed this experiment, we haven't added much noise. Next, let's predict an unknown. Recall I have this array of unknown data where we have our wavelengths and these response values. And so let's pass that in. We're going to read this data/unknown.csv. We're going to store that as unknown.df. The next step, we must then extract the lambda_max value. So we're going to call that a_unc. And lastly, we're going to predict our unknown concentration by solving this equation. We have our absorbance for the unknown concentration. We're going to subtract the intercept and then divide by the slope. And then I'm going to return that as the predicted concentration with this F string. When we do this, we can see that the predicted concentration is 7.0. Now, I could tell you that's pretty close to what the actual value is because I helped to design this data set, but we can also visualize this output in a number of ways. One way is just to actually show the curve of our unknown sample related to the standards. So I'm gonna do that by melting my standard data frame, and then we're gonna plot two different plots overlaid on top of each other. The first will be our standards, then I'm going to add the unknown data as a black trace on top of that. I'm illustrating with this black line our unknown sample, and it appears between standard 4 and standard 3 here in green. Standard 4 was at concentration 8, and standard 3 in green was at concentration 6. And so a predicted concentration of 7 actually fits this data quite nicely, and we gain this intuition visually as well. Lastly, I want to demonstrate how we can take our parameters B0 and B1 with any new value and predict a new concentration. So let's say you're performing this experiment in a lab and you have new data flowing. We can pass the data into these fitted parameters and get a new predicted concentration. So let's say we have an absorbance of 0.2 at our lambda max. We can predict that to be 1.977. based on our model parameters. Next, let's say we have an unknown value at 0.4, and we want to predict that as well. We see that the predicted concentration is 3.98. So by going through the exercise of building out a Python script, we can take all of that hard work and easily reapply it to a new data set. If you enjoyed this video, like, comment, subscribe. If you have any other questions, let me know in the comments below, and I'll see you in the next video. Peace.